class content is three numerical models. So starting like things like that. So if there's any times left, which there might not be, then we'll look at see if there's any questions on the first homework problem. And at this point, only the first problem is what you should look at because we haven't gotten to the other stuff yet. Okay, need my glare boundary. All right. So continuing the heat equation. Okay. A couple things I want to bring back from last time. The fundamental solution five xt or pi t n over 2, where n is the number of space dimensions, minus x squared over 4t. Yeah. And that is the solution of this problem. T is velocity in view. All of our m and positive t, and then we have no boundary conditions because it's a free space problem. And the initial data is the Dirac delta function. I just realized I'm reading for some. This is something that is not in today's notes. And okay, yeah. All right. Now, what I done last time, okay. Oh, and then solution of general initial data. The initial data is a general function of x. Same domains. Is this integral of the fundamental solution x minus y. So it's a convolution. So it's by convolution of u naught evaluated at x. That's the most concise way to express it. All right, so that is where I stopped last time. So now I'm going to solve the different problem. So ut minus the velocity of u, instead of being equal to 0, it's equal to some function f of xt. And for simplicity, we'll assume the initial data is 0. Domains that's the same free space problem is given by and there's going to be a close relationship between the solution I'm about to write and the solution we have here. It's the integral from 0 to t of the integral over all of Rn, where we have this fundamental solution again. But actually, I'm going to write this here a little differently because this accounts for the x dependence, but I need to account for t. So it'll be phi of dot comma t is u of xt. The dot here is meant to be a placeholder for your spatial variable. So that's why I don't actually fill in what it is, because if I say x, that's not really accurate because the x is what we have here. So we're taking this function, this is evaluated at t convolution. The result of the convolution is evaluated at x. Okay. But now, instead of evaluating this fundamental solution at t, like I have here, it's t minus s, where s is the variable of integration for my outer integral. That's with respect to time. All right. And then this is followed by my source term f, evaluated at, oh, this should be y right here. Sorry about that. Okay. And then the time value for f is s, dx ds. So s is going from 0 to t. So the source term f is evaluated at s, and you can think of f of ys as serving as initial data that the fundamental solution is applied to at t equals s, and then this part, which performs the evolution of initial data to your solution at your current time. Since it's starting at time s, we're evolving by t minus s, so that we end up at t. So it's almost like, so one way to think about this, it's this superposition. At each instant in time, we have this source, f of x s. So if you think of s as being your particular instant in time, and that initial data is evolved to time t, but this is happening at every instant. So all of the contributions of a source term, starting at time 0 up to time t, all of those contributions are evolved from wherever they are introduced up to time t. That's why we have the s here and the t minus s here. And it's the integral from 0 to t that is combining all of these contributions. Now, another way I can write this that is similar to what we have here is the integral from 0 to t of the convolution of phi t minus s, convolution with f, again, a dot is a placeholder for a spatial variable, s, evaluated at x. Yes. So this convolution accounts for the integral that's sorry, I'm just running wrong things all over the place here. dy for both integrals. Sorry about that. So this might make it easier to understand what I was saying earlier. That because we see here we have initial data that gets evolved from time 0 to time t. Here we have initial data introduced at time s, also evolved to time t. But because it's introduced at time s, it's evolved over a shorter time span. And then all of those contributions of f at each time, each instant in time, are summed up by this Riemann sum represented by this integral. So the solution of the inhomogeneous heat equation can be described in terms of solutions of a homogeneous problem involving the source term, which is introduced at each instant in time. Okay. This is called Duhamel's principle that describes the relationship between the solution of an inhomogeneous PDE and the corresponding homogeneous PDE. Now here we have initial data and no source term. Here we have source term but no initial data. If we have both, then you just add these two. Since it's a linear PDE. Duhamel's principle is also known as variation of constants, but that term isn't used very often that I've seen. Probably an easier way to see why this is a correct formula is to relate it to what you may have seen in your first ODE class. Now this is related to the solution of a linear first order ODE y prime is equal to py plus some function qt. Qt is playing the role of the source term in this ODE. And initial data. So what is the solution of that? Well, first you account for the initial data. In this case, it would be e to the pt. Why not? And then to account for the source term, you have an integral from 0 to t of e to the pt minus s, source term evaluated at s ds. So it's the same idea that in this integral, the source term is treated like initial data at each instant in time, from s equals 0 to s equal t. That source term introduced at each time is evolved from that time all the way up to time t. All those contributions are added together through the integral. So here we have, like, you think of this as like an ODE version of Duhamel's principle. And then here it is for PDEs. But the idea is the same, that we're summing up all the contributions of a source term at each instant in time evolved to the current time t. So any questions about what we have here? All right. Now, before covering heat equation, I covered Laplace equation, Poisson's equation, and saw how solution of the Laplace equation satisfies a maximum principle. And we have something similar for the heat equation. Now, So suppose my spatial domain is omega. Let's suppose it's bounded. No longer dealing with a free space problem. Then I'll define domain omega of capital T. So I'm defining the spatial domain with my time domain. I keep the product with the interval from 0 to capital T. So capital T refers to my final time. And then normally this is referred to the boundary of omega t. There's a boundary symbol here. Although I'm actually not going to include the entire boundary. So this is a slightly incorrect definition, but it's for convenience. So because your domain omega combined with the interval in time, it's something you can think of it as like a warped cylinder in a way. So a boundary, you think it would consist of the bottom and top of the cylinder and also the sides. We're going to exclude the top. So I'm going to include spatial domain along with t equals 0 and the boundary of omega along with the interval 0 to t. Actually, this will be the open interval. So then the top, which would be omega Cartesian product capital T, is not included in this. Okay. So I guess that's technically not the boundary, but I'm going to use that label anyway. Otherwise, it'll just get too cumbersome. Okay. Let's suppose that U x t is a solution of this problem, where we have heat equation on domain T, and then we have initial data. Okay, and then we also have boundary data, Dirichlet conditions. All right. Then we have, as with the Laplace's equation, we have a weak and strong maximum principle. So first we have the weak maximum principle that states that the maximum of U on the closure of omega t, meaning including both interior points and boundary points. Remember, bar means closure, is equal to max on this incomplete boundary. So in other words, the maximum of U can be found either where the initial data is at t equals 0 or along the boundary of a domain omega. Then we also have a strong maximum principle, and just like the Laplace's equation, it applies if omega is connected. So that says that if the maximum of U on the closure is assumed anywhere in the interior of omega t, the only way that can happen is if you use the constant function. All right, so very similar to what we see from Laplace's equation. Okay. Now you may recall Laplace's equation, applications of maximum principle. You replace, and we have similar things here. If you were to replace with minus u, then you obtain what's called a minimum principle. So you could have all of this that's replacing max with min. Also, the solution of this problem is therefore unique. Because any two solutions of this problem would have zero boundary data, zero initial data. So u would be equal to 0 on this entire boundary of its incomplete boundary of omega t. And since the maximum minimum must both be assumed on that boundary, you would have to equal 0 in the interior also. Okay. So same idea as what we've done with Laplace's equation. And lastly, if omega is connected, so a strong maximum principle is applied, and if your boundary data G is equal to 0, then we have the following, that if your initial data U naught is non-negative on omega, then U is strictly positive in omega. Actually, omega t. Right. Something doesn't look right on in my notes. Boundary data is 0. Okay. Okay. Now weird now. I don't recall this coming up. I taught this class in 2021 and 2019. I guess I scrutinize different parts of my notes every time I teach it. I'm gonna check something here. Oh. Okay. Yeah, my notation's a little different. Okay, so is equal to U naught. Oh yeah, that's initial data. 0. Okay. 0. Okay, so that is in omega t. Okay, and define boundary omega t to be okay, got it. Okay, so thankfully, what I've written on the board is correct. My notes for this part is not. So I'll have to fix that. It should also be emphasized that not mentioned in the MIT note either. It needs to be an open set for all this to work because that way boundary of omega t, or I should say omega t, therefore does not include any points in the boundary of omega. Okay, so now everything's good. Okay. And the way that this could be interpreted is, well, actually something I was talking about last time, the heat equation, infinite speed of propagation. Okay. So I was giving an example last time of an initial data that is 0 over most of the domain, except maybe in a small area. And then as soon as t gets positive at all, no matter arbitrarily small, the solution will be strictly positive everywhere. Unlike a wave equation where there's some propagation happening. Okay. So any questions about heat equation and its behavior? Yeah, the thing that's throwing me off about this statement was, okay, this can only be valid if omega t excludes the boundary of omega, because it's already stated from here that u is 0 on the boundary of omega. So as long as I say omega is open, then this domain here does not include the boundary of omega. So then the statement is valid. If omega is not open, that can mess things up a bit. Okay. All right, so we've seen Laplace's equation and the close relative Poisson's equation. Now we've learned some things about solution of the heat equation. Last one deals with a wave equation and its close relative, the transport equation. Okay. So the transport equation is an advective problem. So the first order in time, PE, the UT plus some vector B dot product with the gradient of U is equal to 0. Now we see a one-dimensional version of this already, like UT plus AUX is equal to 0, something like that. But this is the multi-dimensional version. And so X, so no boundary conditions, X nor N. And then we have some initial data. Now this vector B is called a direction field. So it indicates the direction in which the initial data is going to propagate. Okay. And we're going to assume it's a constant vector. So the solution of a transform equation is your initial data evaluated x minus, x is a vector, so it's like b, so vector signs in both. Okay. Is x minus bt. So b, you can think, is indicating speed and direction of propagation because it's a vector. Okay. To see why this is a solution, I take the derivative of this with respect to t. So du dt would be equal to the gradient of u naught at x minus bt. And then you take the derivative of this with respect to time. But this is a vector valued function, so the derivative with respect to time is going to be a vector. So we take the dot, so what because the chain rule, you have a derivative of your outer function, derivative of your inner function, and you multiply them. Well, same thing's happening here, except the multiplication is a dot product. And a derivative of this with respect to time is going to be minus b. So our PDE is saying ut is equal to minus b dot product of the gradient. As long as everything is real valued, dot product is commutative. And the thing is, this right here is u of xt. So sure enough, ut plus b dot gradient of u is 0. And the solution is verified. Now, if I want to solve the inhomogeneous problem, so that would be ut plus b gradient of dot gradient of u is equal to f function f of xt, a source term, and then you still have some initial data. Now I can use this solution to obtain this solution by way of Duhamel's principle. Now, Duhamel's principle was introduced for the heat equation, but it can apply for all kinds of time-dependent problems. Okay, so the solution turns out to be xt is equal to, now the part involving just the initial data, not the source term, we're gonna keep this part. Okay. And then we're gonna have a term added onto it to account for the source term. So that'll be an integral from 0 to t. And so remember how Duhamel's principle works. You're going to take the source term, evaluated at time s, for every s from 0 to t, treat it as initial data. So that means we're going to have f here, evaluated at time s. And then you're going to solve it from time s up to time t. So you're evolving it over a time span t minus s. So if we take our q's from here, that would mean we'd have x minus the vector b times t minus s. Questions about how we got to this? Okay. So now the goal is to use this solution to the transport equation to solve the wave equation, which is a PDE that is a second order time derivative, by breaking it down into two transport equations. Now this is in multi-dimension. We're going to scale this down to one dimension, where the vector b is now just going to be a scalar. Okay. I'm going to attempt to leave this here because I'm going to need it. Calls me to run out of room. I'll just put a box on it and work around it. Okay. All right, so now the what's source term here? Okay. Actually, yes, it is what I'm going to do. So, wave equation. So the UTT minus UXX, so this is in one dimension, equals 0. And then we have at time 0, two initial conditions because it's second order time derivative. Okay. Now what I can do with this, since each of these has I can write this as time derivative operator squared minus spatial derivative operator squared, all applied to u, and that must equal 0. What can I do with the difference of two squares? Well, I'm not. Yes. Okay. Difference of two squares. Yeah. So now we have. I'm going to abbreviate this. Partial t plus partial x times partial t minus partial x of u is equal to 0. So we're factoring the wave equation into two first order PDEs. Now, the only reason this can be done now is differentiation in respect to time and differentiation in respect to space commute with one another. Otherwise, this wouldn't quite work out. So there are not too many PDEs that we can reliably do this to. So by factoring it, I'm going to solve this one first order equation at a time. Okay. So this right here, ut minus ux, I'm going to call that b. So then We don't know what v is yet, but what we do know is that it solves this equation. Vt plus Vx is equal to 0. So but that's a transport equation. With our vector b is just a scalar 1. Well, we know what that solution is. Kind of. We know. So v of xt is some function a of x minus t. Now, we don't know what a is yet, but at least we have a start. Okay. So now I have this equation to solve for u. Since ut minus ux, I'm calling v, and that is equal to a of x minus t. I now have an inhomogeneous transport equation to solve. So this is inhomogeneous transport with b now equal to minus 1. Whoops, sorry. What's my mistake?
There was something specific you said before UX.
Okay. But what's wrong with this equation?
Explain something before.
I have no idea what you're referring to. Please help me.
I watched the video.
Okay.
I'm looking for some specific words.
Okay, yeah, that's gone. All right.
Sorry.
Where did I mess up here? Do you mind how v is defined? Oh.
B was
Yeah. So what's the mistake?
the negatives.
Yeah, it should be minus. Yeah. And that will lead to a transport equation of b equal minus 1. Unlike v satisfies transport equation of b equals plus 1. Vt plus ux is 0. Ut minus ux equals v. All right. Now, I know the solution of this because it's right here. This general solution for inhomogeneous transport equation. Okay, so I'll go ahead and fill that in. So u of xt is equal to its initial data, which in this case is g. That'd be g of x minus bt, but b is equal to minus 1. So I get g of x plus t for the first term. And now I'm going to have an integral from 0 to t. And what I'll put in here is my source term. My source term is a. Now, the thing is, the source term is supposed to be evaluated at this spatial variable, and s is the time variable. So the spatial variable is going to be x minus b, but b is minus 1, so it's going to be plus b times t minus s. But this will be a of x minus t. Now the spatial variable x here is replaced by all of that. And then minus the time value, which is supposed to be s in this case. So I subtract off s here. All Oh. Yeah. Yeah, I had to fill in b is equal to -1, okay. Plus t. Okay. ds. All right. Wait. Minus, yes. Okay. Question about how this is arrived at. Now, this becomes x plus t minus 2s. Now, I'm going to label this as I'm going to let this be y. I'm going to make a u substitution, or I guess we can call it a y substitution. Okay, I can erase this now. Now that I've used it. Okay. All right. And my original variable integration is s. So now I have dy is equal to -2 ds. Okay. So now my solution is u of xt equals g of x plus t plus, okay. Better be careful about this. Plus, I have an integral a of y dy. Now, ds, it gets replaced to -1/2 dy. So now I have -1/2. What's left is to fix the limits. So what I do is I substitute s equals 0 and t into this to get the new limits in y. So if I substitute s equals 0, then y equals x plus t. And then if I substitute s equal t, I get x plus t minus 2t. That's x minus t. So these are my new limits. What should I do now, though, to make this a little less strange with this integral? Because my lower limit is greater than my upper limit.
We can change the limits and change this.
Yeah, so I can make this a plus, then I'll have x minus t down here and x plus t up here. All right. So we're getting somewhere. The problem is we still know what a is. So for that, what I need to do is take the derivative of this whole equation with respect to t, because I have one part of the initial conditions, one initial condition involved here, but we have du dt at t equals 0 must be equal to h of x, and that's nowhere in here. So to work that into it, I'll take the derivative with respect to time. the ut of x0. So now I take the derivative of this with respect to t. So that's going to be g prime of x plus t times the derivative of this with respect to t, which is 1. And then I said t equals 0. So I'm just going to get g prime of x right there. Then I take the derivative of this with respect to t. Now, you're taking the derivative of an integral with respect to a certain variable, and your limits depend on that variable. Do you remember how that goes? I'm taking a derivative of this integral with respect to t. My limits depend on t. So what happens when I take that kind of derivative? It's a fundamental theorem of calculus thing. I might not have seen this since Cal 2. Well, we have 1/2. And what we'll have is the integrand evaluated at the upper limit times the derivative of the upper limit with respect to t. But that's going to be 1 in this case. Minus the integrand evaluated at the lower limit times the derivative of the lower limit with respect to t, which in this case is -1. Yeah, so fundamental theorem of calculus combined with a chain rule gives that result. And then I evaluate that whole thing at t equals 0. But this is gonna be a of x. And then when I plug in t equals 0, this is also gonna be plus a of x all over 2. So I end up with g prime of x plus a of x, and that has to equal h of x by the initial condition. This initial condition here. So now I know what a of x is. That was the missing piece, my solution. So now what I would need to do is go back here, replace a with the formula that I now have for it, and see what I get. Okay. Let's see. Okay. So now u of xt equal to g of x plus t plus 1/2 integral x minus t to x plus t of a of y, but that is h of y minus g prime of y. But now the integral of g prime, that's just going to give me g. So I'm going to have g of xt, x plus t again, minus 1/2 g of y, evaluated at limits x minus t and x plus t. And then the rest, we're just going to leave as is. The integral from x minus t to x plus t, h of y dy. So the only thing left to do is plug in the limits. So I'm going to get g of x plus t minus 1/2 g of x plus t. So I subtract off half of it. So now I have 1/2 g of x plus t. And then I'm going to have minus a minus g of x minus t over 2. So I have 1/2 times all of that. And at last I am done. Barely fit a box around this. Okay, so that's the solution. Anyone happen to know, maybe from another class, what the solution is called? It's named after someone. The limit solution. Sure, I'm not pronouncing it right. Okay. It's actually a much easier formula to work with than the solution of the heat equation, where in that case you have a very difficult integral to deal with. Okay. And if there had been there's no source term in this problem. If there had been a source term, there would be another integral here, and that would come from Duhamel's principle. Could be used to work out what that is. Okay. Any questions about what happened here? All right, so this is for one space dimension. But I can say something about the solution in higher spatial dimensions, at least 2D and 3D. There's some interesting behavior that comes about from that. What's very strange is it's actually easiest to get 3D first and then get 2D. All right, so we have UTT minus Laplacian of U 0. Then we have additional conditions, U is equal to G, UT equal to H. So the solution is given by what's called Kirchhoff's formula. All right. So we have xt is integral over the boundary of a ball centered at x with radius t. Then we have e times the second initial data, corresponding to du dt at t equals 0, plus the first initial condition, g, plus the gradient of g, dot product with the vector y minus x. Right, I'm going to rewrite this because I have no room. So. I can't just say dy, because dy don't imply integral Cartesian coordinates, because this is a boundary of a ball. So this has to be the element of area on the ball. So let's take that into account. Okay. So b of xt is a set of all x such that there's all y such that distance between y and x is less than t. So the boundary would be this, where distance between x and y is equal to t. Okay. Seems like a fairly simple formula, but evaluating the actual integral will be quite difficult. Now, to get from the 3D case to the 2D case, what you do, and this is something I worked out in Math 417, 517, because I was thinking that in that class, I also derived the leverage solution, but in a very different way than what you see here. Well, I think the way I just did it, I find that more appealing personally. Well, I guess they both have very appeal different ways. That if you think of your solution, your initial data, as not depending on z at all, so functions of x and y only, and you transform this integral, which in 3D would be over the boundary of a bounding sphere, and you transform it into an integral over a disk. So basically, you're taking the sphere and flattening it to the disk. That's called the method of descent, applied to Kirchhoff's formula. Okay. What we get is, so Kirchhoff's formula is Poisson's formula, or Poisson's integral formula. And that is t is 1/2 roll over. Now it's just not the boundary of a ball, but the interior of a ball. And we get part of the expression that you recognize from this integral plus t squared to y plus t radiant of g. Dot product of, oh, I goofed, this is y minus x, not x minus y. All over this diagram 0 type expression, t squared minus y. Okay. That's the formula in 2D. Yes.
So I don't get the interpretation of the ds y bar.
Yeah.
What's the interpretation?
Okay. Okay. So since this is 3D. Okay. So for any point that sits on the sphere, of radius t. It's like the area of a patch of that sphere. So just like in an ordinary integral, you have this dx, so it's an element of length. Since this is basically on a two-dimensional entity, it's an element of area. So, because think of it this way, if you think of a mapping of, say, like a rectangular square to like the northern hemisphere, there's going to be some warping there to get from a patch of a rectangle to a patch on a sphere. So that ds of y takes that into account to have a proper area, like the weighting for your integrand. Yeah. If you, so for what you would really do is spherical coordinates. So actually, this would work out to t squared sine phi d theta d phi. So actually, I can go ahead and write that. Should have said that at the beginning. Yeah, fair. All right. And then the integral would be theta from 0 to pi, 0 to 2 pi, phi going from 0 to pi. Okay, any other questions? Whereas this integral will be in polar coordinates, so you'd have r d theta. But whereas this is only considering the boundary of a sphere, this is the interior of a ball. So we end up with very different behavior in, yes?
You just said interior of the ball.
In, yes, so like disk,
So,
yeah.
that is.
Whereas it's like the outer casing of a ball. Okay. Yeah, because otherwise I'm thinking ball, I'm thinking and how many dimensions you have. Okay. So I can show you a couple examples, one of each, in two-dimensional, three-dimensional, with certain initial data, to give you an idea as to how differently the solution behaves in 2D versus 3D. Oh, sorry, what?
The last part.
Oh, what I just said?
Just
Okay, hurry up. Okay. One thing is, I remember when I discussed Kirchhoff's formula, and I forget which class it was, like it could be 517 or 606. I don't remember assembling what I just wrote. Obviously, they had to be equivalent, but okay. So as an example, for initial data, let g be equal to 0 and h be equal to the Dirac delta function. So then the integral simplifies considerably because we get u of xt is equal to the integral over boundary of the ball, center f, x radius t. Okay, we get all right, so t delta of y. G is 0. Actually, okay, everything else is 0. And in this case, what that evaluates to is 1 over 4 pi t squared, which you can think of as, remember, that's the surface area of the sphere, times t. And this is for magnitude of x is equal to t and equal to 0 otherwise. Okay. So really it simplifies to 1 over 4 pi t. So So remember, the delta function is equal to 0 everywhere except the origin. So how the solution behaves, this is called a sharp front. So at any given instant in time, the solution is still 0 everywhere, except it's equal to this constant value on for x sitting on a sphere of the correct radius. And that radius is always increasing. So you have your solution, you can think of it like as a point at t equals 0, and it keeps expanding. But it's a sharp front, meaning that once this front passes a certain point, then it's 0 there again. So the front moves on, and where it had previously been, the solution is 0 again. So if you put yourself at a fixed x, somewhere in three-dimensional space, a fixed point, then first your solution is 0, 0, 0, but the front comes, and for an instant, your solution is non-zero, it's equal to 1 over 4 pi t, and then at the point where you're observing, it goes back to being 0 and stays 0 forever, because the front is gone. But now I want to contrast that with the 2D case. All right, so g is equal to 0, so that wipes out most things. I have 1/2 integral over the ball over the disk, center x radius t, and I'll have t squared delta function. Actually, that's everything. Yeah, everything else in the numerator is 0. And we have t squared minus x squared raised to the 1/2 dy. Okay, and so what that reduces to is okay. So y has to equal 0 for this to be non-zero at all. And so what we get is 1 over 2 pi t squared minus magnitude of x squared all to the 1/2. And this is for x magnitude less than or equal to t, and then 0 for magnitude of x greater than t. Okay. So what does this mean? Again, suppose you're at a fixed x somewhere in two-dimensional space. Well, initially t is 0, so you're in this situation. Magnitude of your point where you're observing is greater than t. So your solution is 0. So it stays 0 until this amount of time passes equal to the magnitude of your point. So once t hits your magnitude, now the solution is non-zero. And as long as t is greater or equal to the magnitude of x, you're going to have something here. So your solution, once it becomes non-zero, stays non-zero forever. It is not a sharp front. So once the wave hits you, you feel its effect ongoing. Unlike this case where it moves on and you're left alone. So totally different behavior in 2D versus 3D. This is called, I'm not going to pronounce this wrong also, Huygens principle, that this sharp front behavior is what you tend to see in odd dimensions, except for n equals 1. And then this kind of behavior is what you get in an even number of dimensions. Okay. Alrighty. Oh, it's exactly the end of class time. And that's the end of all the pre-numerical stuff. So we very much shift gears on Tuesday. Sorry I haven't run any homework questions, but I guess you might not have been working on it anyway. Yeah. Or have you? Oh, how's it going?
Stops in the middle of working,
Okay, well,
but I have to say.
okay, we'll definitely have time later anyway. All right. Yeah, plus, you all know you can ask me questions whenever, so. And I guess if you find out what specific thing you're wondering about, let me know. Sorry, if you had to watch the video to find it, but,
I will.
okay.